Alright, so this is activity 3.3.4, kind of a second example of an optimization problem. We've actually looked at a similar one before. We have a piece of cardboard that's 10 by 15, and we want to make a box out of it. And so we're going to do that by cutting a square from each of the corners, right? And then the sides are folded up. So the box needs to be at least 1 inch deep, but no more than 3 inches deep. What's the maximum possible volume? And I should say our box does not have a top. So how is the box actually made? So here's the box. We cut a square from each side, or from each corner, and then these are the edges that you're going to fold up, right? And so by folding it up, you end up with a box like this, right? You can see on the inside. Good. So I guess we're starting with a cardboard box that's 10 by 15, so let's just go ahead and make this side 10 maybe, and this side 15. Good. Now when we cut a square out of each side here, that means that a square is going to be, we could think of it as x by x, right? And so when you look down here at this box, where is this x going to be? The x is going to be the height of the box. Okay, and so then this length right here, maybe I'll draw it in red. This length right here is this length right here, right? And so that length is going to be 10 minus 2x. Good. And then this length right here is, let's see, I don't have another nice color here, so that's not going to work. I'll just use red again. But it's going to be this length right here. Okay, that's what this side is. And so that's going to be 15 minus 2x. Okay, so therefore the volume of the box that we're going to try to maximize here, volume, is going to be the width times the height. Well, x times 10 minus 2x times 15 minus 2x. Good. Yeah, so that's pretty straightforward. That's a cubic polynomial. And so let's see, what are our other restrictions here? We're told that the box needs to be at least 1 inch deep, but no more than 3 inches deep. X is the depth, right? So that means that x is running from 1 to 3. Okay, and so when we make up our optimization problem, this is a continuous function over a closed interval, right? And so we're going to need to find both the critical points and our endpoints, and then we'll write down our x's and our volumes. So far we have 1 and 3, right? Those are the two endpoints, and then we have to go through and we have to find our critical points. Okay, that's going to take a little bit of work since we have a triple here, but it shouldn't be too bad. Let's see, v prime is equal to derivative of the first function times the other two, which is 10 minus 2x times 15 minus 2x, plus x times the derivative of this guy, which would be minus 2 times 15 minus 2x, and then the derivative of the last one, which would be a minus 2. Okay, and now we set all of this equal to 0 and we solve. Let's see, this is going to be a quadratic, it looks like. So I'm going to pause for a minute and simplify. Okay, looking at the algebra, I think it actually would have been easier if we would have simplified our v first. So let me just go ahead and redo that. Well, you could do it this way. The algebra is just a little bit messy. So let me go ahead and take my v. If I multiply this out, this is 10x minus 2x squared. And then if I multiply it by 15 minus 2x, I will get something that's a lot simpler. V is just going to be 4x cubed. minus 50x squared plus 150x. And you see that's a lot easier to deal with than that. Okay, so we just have this cubic function. And now the derivative will be a lot easier to compute. So the derivative with respect to x will just be 12x squared minus 100x plus 150. Okay, now we're going to use the quadratic formula and plug that into our calculator, I guess. We're going to end up with 25 plus or minus 5 square roots of 7 over 6. And so the two values end up being approximately 6.37 and 1.96. Okay, and of course we see 1.96 is inside of our interval, but 6.37 is outside. Okay, and so we'll just work with the 1.97. Good, and now we just plug these into our V here, and I will pause while I do that on my calculator. Alright, so I've got some numbers here. When I plug in 1 into my volume function, either one, I get 104. And then if I plug in 3, I get 108. And then when I plug in 1.97, I get approximately 132. Okay, and so on this interval from 1 to 3, it looks like this is going to be our max, and that will be our min. Good. Now I should say, if the 1 and the 3 had not been given, is there a natural domain for this function? Well, clearly x has to be bigger than 0, right? Because otherwise our height would be greater than not greater than 0. And then this means that 10 minus 2x, right? If x is between 0 and 5, then we have a positive height here, or this length, whatever that is. And then for this one, x has to be between 0 and 7.5, right? And so the kind of the natural domain here is that x has to be bigger than 0 and less than 5. Okay, so if you actually look on the if you graph our function v, what you're going to see is the function comes up and down, and then it actually comes down around like this, and this is from 0 to 5. And then let's see, we got our maximum at 1.97, which is about 2, right? Good. And so our restriction is like, about here and here. So this is from 1 to 3. Okay, and so that's explaining what the numbers are here that you're seeing. Good. So if I had not been given the 1 and the 3, I would have gone for 0 and 5 for my two bounds, and then the middle point would have had to have been my maximum, right? Because if it's any positive number, it's going to be bigger than 0. So okay. So again, the maximum possible volume is 132 in this case, and the minimum possible volume is 104. Very good.